So I'm sure you noticed that we got cut off there. So let's carry on. And so we were about to start the problem, the derivative of 4 to the x to the fourth power. So this is one of those cases where we have to decide which form this takes and which formula we should be using. In a case like this, though, it turns out, though, there is one way that we might be able to make it a little easier on ourselves, and that would be this identity, a raised to the g of x power equals e to the g of x power times the log of a. Okay, so if we use this approach, then we can rewrite this function as e to the x to the fourth times log 4, and then we need to take its derivative. And now here we can go find the function that we need. What we're doing here is taking the derivative of e to the g of x. Okay, by the way, don't forget log 4 is simply a constant. So we can think of this as very simply x to the fourth times log of 4. So let's go back to our list of rules. Well, let's see. Do we have one here? Yes, we do, but it's way, way back. What we're doing is this. All right, here it is. Here it is. Okay. It's e to the g of x times g prime of x. In other words, by writing it like this, what we're doing is we're using this rule instead of one of these rules back here. Okay, in other words, we could have used this one directly. Whether this is simpler or not, what we're about to do is a matter of opinion. But let's try it this way. All right, so if that's the case, since a to the g of x is e to the g of x log a, this 4x to the fourth, as we've seen, is equal to e to the x to the fourth log 4. And now what we're going to do is take this d for dx, e to the g of x becomes e to the g of x times g prime of x. Okay, so if that's the case, then g of x is this exponent right here. Because of the definition that we used, e is now being raised to the x to the fourth times log 4 power. That will become our g of x. Now, the derivative is easy because, like I said, this is a constant. So based on the power rule, we'll simply end up with 4x cubed log 4. So now, here's our e to the g of x. And this entire expression is g prime of x. And that's the final answer. Okay. If you want to, and by the way, remember this identity that we used. If you would prefer, this e to the x to the fourth log 4 can now be replaced with the original expression, which is 4 to the x to the fourth power. So we end up either with this as our answer or this. Either way, we have the same thing. Now, of course, by writing it like this, you could see that what we could do is something like this, which is maybe a little bit simpler, but that would be, the main motivation for rewriting it like this. All right, now, what about the integrals? So here we have the integral of 3 over 2 to the 3x power, which you can see can be rewritten as 3 times the integral of 2 to the minus 3x power. Now, which rule is this? Well, we've got a to the g of x dx. So what rule would that be? Well, why don't we try this? Let us try the method of substitution. So let's have u equal negative 3x. Then du is minus 3. Du dx is minus 3. Du is minus 3 dx. So what does that leave us with? All right, so we've decided that u is minus 3x. And therefore du, as we've seen, is minus 3 dx. Now we have the 3. I mean, you could rewrite this as Oh, oops. But we need a negative there. So what we'll do is we'll supply it ourselves. We'll put two negatives in here. And now what we have here is very simply minus 2 to the u du. Now, what do we do with this one? A to the u du can be written as, let's see, this rule tells us that we can rewrite this as a to the u du. Okay, so u is here. So a is 2. We have u already 2 to the u power. And we have the du because we have the net negative here. So according to what we're seeing here, 1 over log a would be 1 over log 2. Here we have 2 to the u power. We, of course, need our c. And then we can replace u with its definition of negative 3x. So the final result is negative 1 over log 2 times 2 to the minus 3x plus c. Okay. So in other words, this rule implies that we can also write this as a to the u du is 1 over log a to the u plus c, and that's what we have here because the exponent is negative 3x, which is a function of x. Well, now we're going to revisit our old friend L'Hopital's rule. Okay, well, you've already seen how to use it to obtain a limit when direct substitution results in what we call an indeterminate form, such as 0 over 0 or infinity over infinity. Now, it turns out there's many other indeterminate forms that we might encounter, and it turns out that we can typically apply L'Hopital's rule in every one of these cases. So if you find that with direct substitution, you're getting one of these bizarre cases, the first thing you might want to think about is using L'Hopital's rule. And of course, you remember what it is. It tells us that if we have a limit of some kind where x approaches a, which could be infinity, by the way, or negative infinity, then this ratio can be replaced with f prime of x over g prime of x, and we'll get the right answer. It's a very helpful rule. Now, it turns out that we can actually apply L'Hopital's rule more than once. If applying it brings us to another indeterminate form, sometimes the way to go is to simply reapply it. So here's one of those cases. Now, if you look at it, direct substitution is going to leave us with a mess. Now, the numerator, of course, it's squared. So that's not going to be negative infinity. What we actually have here is positive infinity over positive infinity. Not good. So what do we do about it? Well, let's try L'Hopital's rule. So in this case, the numerator f of x is x squared. So by the power rule, actually the power rule applies to polynomials, not the second one. So let me just erase that. But you get the idea here. Now remember the way it works with e to the x. By the chain rule, this is what we get. So here we have e to the g of x. Well, actually, that's kind of awkward that I'm using the same letter. Let me change it to h. So e prime, this is e, yeah. Let's say g of x equals e. Okay, so g prime of x would be e to the h of x times h prime of x. So here h of x would be this negative x, and h prime of x would be negative 1. So anyway, consider where they came from then. Um, that means we end up with e to the minus x times -1, which is the same thing as minus e to the minus x. Perfect. So these are our two derivatives. So by applying L'Hopital's rule, we'll end up with 2x, the limit of 2x over negative e to the minus x. Now, unfortunately, direct substitution will lead us into trouble as well here. And yeah, you can see this is what we ended up with. This is our f prime of x, this is g prime of x. But if you plug those in, you're just going to end up with the negatives cancel out. We still have infinity. So you might figure, well, that means we did the wrong thing, but not necessarily. We can try it again. And we can try this now. Oh, yes, we're allowed to do that. We're going to try the ratio of the second derivatives. So f, here we have 2x. Based on the power rule, f double prime of x is 2. And g prime of x is this negative e to the minus x. G double prime of x is going to be positive e to the negative x because it's going to be negative e to the minus x minus 1, which is e to the minus x. So now that ratio may behave a little differently when we take the limit. Okay, so here it is, 2 is our second derivative of f. And then here we have e to the minus x. So let's see what happens with that ratio when we take the limits. So direct substitution, the 2 will stay at 2 in the numerator. Here we have e to the positive infinity. But now here's the interesting part. Because we have a constant over infinity, that gives us a limit of 0. Because in the denominator, the number is getting larger and larger and larger while the numerator is remaining the same. So that means that the limit is 0. And now we have an answer. We don't need to go any further. So in other words, we applied L'Hopital's rule twice, and we ended up with a solution. And of course, there's nothing to stop us from doing it 3 times or 4 times, because eventually one of these terms will end up being a constant, and that is a big help. All right, so that was basically, this is what we've seen before. We already knew that L'Hopital's rule can be applied to cases where we end up with infinity over infinity. It's just that this time we had to do it twice, but it's the same process. What about this case, though? What if our indeterminate form is 0 times infinity? We haven't seen that one before. So far, we've only had 0 over 0 and infinity over infinity. Well, it turns out that this one works too. Okay, so let's see an example of this. All right, so what happens with direct substitution? We have e to the minus infinity, which is 0, because e to the minus infinity is the same thing as 1 over e to the positive infinity, and that's going to just give us 0. This one is just infinity. So here's the form that we're looking for. Now, what do we do? Okay, we haven't seen this before, 0 times infinity. So here's what we could do. We could use our cleverness to recognize that this is the same thing as this. And all of a sudden we have a ratio now. Guess what we can do? We can apply L'Hopital's rule. So f prime of x will be 1/2 x to the minus 1/2, and g prime of x will be e to the x. So let's see what happens when we try to take the limit of that ratio. So Now keep in mind, this numerator could be written as 1 over 2 radical x. So we're going to end up with 1 over 2 times radical infinity. Okay, so we're going to have 0 over infinity, which leads us to 0. So basically, the only thing that really is different here is that we had to rearrange the limit algebraically to put it into the form that we're more familiar with. And so when we took the derivatives, then we ended up with a result. Now, if this didn't work, we could have tried L'Hopital a second time, and if that still didn't work, we would have had to try something different. Okay, what other indeterminate forms are out there that we can use? Oh, here's one. 1 raised to the infinity power. Well, that's a pretty bizarre case. What do we do now? Here it is. Now, why is this giving us 1 to the infinity power? Well, let's look. If you directly substitute infinity here, we have 1 plus 1 over infinity to the infinity power. And well, that's going to leave us with 1 plus 0 to the infinity power, or there we go, 1 to the infinity power. Just what we were worried about. So what do we do about it? Let's try. Oh, now here's a very interesting idea. Why don't we take the natural log of both sides of this equation? Can we do that? Yes, of course we can. So we're going to end up with log y is the log of this limit 1 plus 1 over x to the x power. So because this is a log, we saw this already earlier, that implies that this can be written as log x limit x goes to infinity of 1 plus 1 over x. So in other words, this became the coefficient because it's a log. Well, fine. Now what do we do? Well, here's what we're going to do. Now, you're looking at it and saying, what's going on here? This x, multiplying by x, is the same thing as dividing by 1 over x. So why are we doing this? Well, you'll see in a minute. We're going to take the log of this expression. And by the way, if you notice, the log of this limit is the same thing as taking the limit of the log. So you notice how the log moved inside. And so now we're going to take this limit, and as x goes to infinity, you're probably thinking, well, that's not going to help. But well, you're right. I mean, if you put it in infinity here, you'll end up with 0 over 0. So instead, why don't we take the derivatives using L'Hopital's rule, and let's see what happens. All right, so here's our f of x. And g of x would be the 1 over x. Or, by the way, this can be written as 1 plus log of 1 plus x to the minus 1. So when you take the derivatives, now this one's a little bit challenging because you've got log of g of x here. Remember how that works. End up with g prime of x over g of x. So this is my g of x. So in other words, you can rewrite this as 1 over g of x times g prime of x. So this is 1 over g of x. What about the derivative? Well, here you're going to end up with the power rule. So you ultimately end up with minus x to the minus 2 over 1 plus x to the minus 1. And yeah, here it is. In great detail, g prime of x is negative x over to the negative 2. Okay. So let's see. Okay, finally. Oh, wait a minute. What happened here? Oh, I see what happened. That huh, this is kind of strange. The notation is a little weird here. Yeah. Yeah, I see there's f of x's and g of x's flying around all over the place here. I'll tell you what, let's take this out of here. Yeah, that's kind of awkward. Um, because the original function was f of x. So I'll tell you what, let's do this. If we have f of x is this log 1 plus 1 over x, and we rewrite it like this. So this is according to the chain rule for logs. So for just this part of our original problem, this would be g of x. Okay. And again, based on the power rule, we'll end up with minus x to the minus 2. So the derivative of just this term is going to be g prime of x over g of x, which means minus x squared over 1 plus x to the minus 1. But we still need the derivative of this g prime of x, which is right here. We have this 1 over x or x to the minus 1. And its derivative is minus x to the minus 2. So when you combine all of this, the negative x to the minus 2's cancel each other out, and we end up with the limit of 1 plus x to the minus 1. Now we can directly substitute infinity into here. If you prefer, we can rewrite this as the limit. X goes to infinity of 1 plus 1 over x to make it easier to see that because this is infinity, we wind up with 1 plus 0, which is 1. So what did we just prove? Going way, way back here, we saw that the log of y equals this. Okay, great. So we used L'Hopital's rule, and what we've just shown is that log of y equals 1. So if that's the case, not 1, y equals z. All right, so what this means then is that this, which was our original problem, has a limit of e. And in fact, what you're seeing here is the formal definition of e. This is where it actually comes from. This is how it's defined. E itself is the limit as x goes to infinity of 1 plus 1 over x to the x power. That's where it actually comes from. We know how it's related to logs, but this is how it is obtained. It's a limit. That's all it is. Okay. Now, it's interesting how that popped out of this problem. Now, we have a couple more things to do here. We're going to briefly consider how to take the derivatives of inverse trig functions. And so I put together a nice little chart for you here. Okay. So again, when you run into one of these, you really should have a chart like this right in front of you. And so here's a quick example. What if we have by the way, the book likes to call these arc signs. I mean, that's technically what this is. These both mean the same thing. I just want to mention that. I noticed that the book usually uses the words arc sine. It's the same thing. It's the inverse of the sine. Okay. So anyway, here's arc sine 2x. Think of this as g of x. G of x is 2x. G prime of x is 2. So what formula are we using? This one right here. Go back to your chart. You'll see your arc sine formula for the derivative. And so now it's just direct substitution. And you'll end up with g prime of x over the square root of 1 minus g of x squared. G of x is 2x. So this is our final result. Although if you want to, you could rewrite it as this, but of course it's the same thing. So it's just a question of recognizing. I mean, well, here there's nothing to recognize. You've got an arc sine or cosine, whatever the case may be. You're being asked to take its derivative, and you just look it up in this chart and then go ahead and calculate g prime of x, and you're all set. How about this one, the tangent? So again, yes, the tangent is here. It's g prime of x over 1 plus g of x squared. Whoops, wrong one. Okay, so this means clearly g of x is 3x. G prime of x is 3. And so we just do some direct substitution and we end up here. But again, if you want, you can rewrite this as, okay. Now, if you can take derivatives of these inverse trig functions, as they're called, you can also integrate them. Now, we've already started to do some of this. The table in the back of the book has all of them listed. I picked these out because these are the ones you're most likely to run into. And you can see they kind of look familiar. It's a little trickier because you have to recognize when you run into a problem like this that it is in fact an inverse trig function. Okay, here there's no doubt in your mind. It tells you to take the derivative of an inverse trig function, but here you have to recognize it. So for example, let's look at this one. Dx over radical 4 minus x squared. And you look at it and say, that looks awfully familiar. If I think of u as x and a is 2, what I have here is actually du. Oh, and by the way, that implies that du is dx. Look what I have, du over radical a squared minus u squared. So that means that this must be the arc sine of u over a plus c. So now I just have to plug in u, which is x, and a, which is 2. And I'm all set. And don't forget, of course, the constant, because this is, after all, an indefinite integral. All right, one more. Let's see if this looks familiar. It does, but we have to be a little careful here because, yes, this could be written as radical a squared plus u squared in the denominator. The only unfortunate thing is that that means this a has to be a radical, which, it isn't that big of a deal. But just be aware of that. That doesn't stop this from being an arctangent problem just because 2 is not a perfect square. So instead, a is then defined as radical 2. U is 3x, because as you can see, if we square it, we'll end up with 9x squared. So our a is radical 2, and a squared is therefore 2. U is 3x, du dx is, or du is 3 dx. Oh, see, now that complicates things because we don't have that 3, do we? So we have to do one more thing here. We have to supply that constant. And then we're good. Okay, now we're all set because we have du over radical a squared plus u squared. And that's going to lead us to an arctan. All right, we plug in the numbers. So let's see. So applying the rule, now remember, let me just copy this. So now remember, we need that 1/3 because that was required to start the problem in the first place. We need that for our du. But then here we have 1/a. And then we have u/a. And then that's it, we're done. I mean, you can multiply the 3 through here if you want, but basically this is it. All right, so we're done now with chapter 5. It was a very long chapter. And so I have posted a set of problem sets for this chapter. They're on Brightspace. And so the next time we get together, I'm going to go through the solutions and then we'll move on to not 6, but 7. If you look at the syllabus, you'll remember we're not doing chapter 6. We're going directly to 7. Okay, so I'll see you all next time.